today really is focusing on the function model or basic form. Now the basic form is very simple here. It's y is equal to a times b to the x power. And obviously, just like any function, y is our dependent variable, and x is our independent variable. Now I say that because oftentimes we don't, in solving a problem, particularly a context problem or problem we call it, you don't necessarily have to use x or y. You just need to identify what is the independent or dependent variables. So at times when you call for a population over time, then time becomes the independent variable. You will use t, and population you will use p for dependent variable. Now a in this case, we often, this is a constant. Constant means it's a number. B is a constant, right? So they're not variable at all. So oftentimes in a problem like a context problem, you want to be able to have the specific A and specific B to be able to solve for X or Y, right? Now similarly, you will see something like this, right? I earlier said P is equal to A times B to the T. So it looks exactly the same. They just switch out the variables. And oftentimes in a growth model, say over time, you can use Y or use P. So let's say Y the T, Y function in terms of T. You will have a basic model A times 1 plus R to the T power. Now, I want you to just think about it. A is still constant, right? Now, R is a rate of growth, but rate of growth is a very specific number. Then number plus 1 is also a very specific number. So this whole thing is also a constant. So as you can see, even though it becomes a little bit more complicated, it still holds true to the original form, right? A times a constant times some kind of constant to a variable goes back to this original model form. Now, into the decay means something that gets less and less versus growth, which gets more and more. You can also use this y of t, and it's equal to a times 1 minus r to the t power. Now again, constant. This whole thing is also a constant. And depending on what kind of rate that we're talking about, oftentimes you either have to look for it or the problem will provide for you. So in this case, we're gonna, we're gonna provide you a couple examples to illustrate that. So let's start with one example. Example number 1. And the example number 1 here is in a city. Say you got 4.6 million people in the year of 2010. Okay, in a city. And the problem says that the rate of growth is 1.3% a year. Okay. And so then the question says, it wants you to find a particular equation for the population growth in terms of time. Now, sometimes you will see you will hear or a problem will be written as growth in terms of time or growth with respect time, and either way it means the same thing. It means in this case, right, the population growth. In this case, this is a dependent variable. We can call it P, and then time in this case is an independent variable. We can call it T. Now, further analyze this problem, we say, okay, now growth, in this case, growth is R is equal to 0.013, right, 0.013. Now, in this particular case, what I'm trying to tell you, and I'm going to explain this problem in two parts. First part is to show you how when we look at this from a numerical point of view, you will see how this will correspond to the growth model that I have written earlier. Y of t is equal to a times 1 plus r to the t power. You may ask, well, where did 1 plus r come from? So I'm going to show you. So the first part of this problem is not to necessarily solve the problem. I mean, it is solving the problem, but it is also demonstrating to you that this growth model is indeed written in this form. Okay, so it's proving that as well. So here we go. Now, we know that this follows this process. P is equal to a times b to the t power. Right, this is our general equation. But because we don't know what A is, we don't know what B is, we don't have a particular equation. Particular equation is when you figured out what A is and what B is for that particular problem context. So let's take a look at this. Year, I'm going to use the basic table of numbers. And let's see, P over here. So in the year of 2010, we have a population of 4.6. Now this is all in million. 4.6. So that means t is equal to 0. Let's just count it for the purpose of our problem. We count 2010 as t equal to 0 because that's the initial year. 2011 is 1, t equal to 1. So what's the population? Well, population grows by 1.3% a year. So you take the original population, right, and you want to add the extra one, the growth, and the growth is 1.6% on the 4.6 million people, right? So it's 4.6 million times, right, times 0.13, right? Oh no, I'm sorry, 0.013. 0.013. Okay. So if you look at this and you can say, okay, how can I write this in a form that is simpler? You can factor out the 4.6, and you end up with 1 plus 0.013. So you end up with 4.6 times 1.013. So far, so good? So far, so good. Okay, let's go to the next year, 2012. 2012, t is equal to 2. T is equal to 2, so that you end up with, you want to take the previous year's population, which is 4.6 times 1.013, right? That's the previous year, where we ended up with this one. And then is the 1.3% right? 1.3% of that previous year population. So is 4.6 times 1.013, that's the previous year's population, right? Previous year's population, times the 1.3%, which is 0.013, right? So if you do that, you can factor out these two things. Then you end up with 4.6, 1.013 times 1 plus 0.013, which gives you 4.6 times 1.013 times 1.013, which gives you 4.6 times 1.013 square. Okay? Let's go down further and see if we can see some patterns. All right, 2013, which is year number 3 in this case. So year number 3, you have the previous year's population, which is 4.6 times 1.013 square, and you have 1.3% on top of that, right? 1.3% of the previous year, in addition to the previous year population. So it's 1.6, 1.013 squared, and then the 1.3% both, so times 0.013. So then you end up with this, right? You end up with you can factor out this one. So you end up with 4.6, 1.013 squared. You factor out this term, and you're left with 1 plus 0.013. So you end up with 4.6, 1.013. Oh, you won't be able to see the, let me switch. So now you can see the process a little clearer. 1.013 squared times 1.013. Look at this. It's the same multiplier. So we can combine the multiplier. So 4.6 times 1.013 squared. Third, cube. Now you take a look at this. This is surprising, isn't it? Or may not be surprising to you. So if you look back to the pattern, you can almost think of this as year 1, when t is equal to 1, you got 4.6 times 1.013 to the 1 power. Year 2, 4.6, 1. So I'm going to circle this. 1.6 times 1.013 square, right? It corresponds to year 2. And then third year 3, 4.6, 1.013 to the 3rd power. So you can almost go back and say here, in this case, this is, the first year is 4.6 times 1.013 to the 0 power. Well, makes sense, right? Anything to the 0 is 1, so you still end up with 4.6 right there. And so what can we say about this? Well, we can say about this is that, hey, perhaps the P, right? P in this case is indeed 4.6 times 1.013 to the T power. So I now know what A is. I now know what B is. And so I know that this whole thing is my particular equation for this particular context, the city population growth in particular. Now take a look at this. When you match up with a growth model, wasn't it earlier says y of t is equal to a times 1 plus r to the t power? Hey, that makes sense because you got rate of change is 0.013, and 1 plus 0.013 is indeed 1.013. Now A in this case turns out to be is 4.6 million people in 2010, and is in this particular case our initial condition. So here what's the conclusions? Conclusion is this, is that in the exponential model form, this constant A, is always going to be whatever the beginning value is. And then we then can figure out what the B is. Does that make sense? So here is our solution, our answer. And this answer, as you can see, as I explain this process, I hope that you catch up on some of the key concepts here. Okay, so now I'm going to go on to the next problem. Example 2. Example 2. Let me bring out my face here. All right. Now, example 2 has to do with a real world problem, world population. I went on the internet and I have just Google some world population values. What I saw was in 1822, the world has 1 billion people, and in 2022, we have currently 8 billion people. So question is find a particular equation for this population growth. Okay, let's just call that part A. That's part A is finding the particular equation. I'll tell you what the part B will be. So if we want to do that, again, use some table to help us to organize these data, right? So number of year, but that's, time and people. This is in billions. So year 1822, we call that t equal to 0. We got 1 billion. And 2022 is 200 years later. We got 8 billion. Okay. So we know this is a population growth problem, and this is, P is equal to A times B to the T power. That's our general equation. But I want to find a particular, so I need to find A. And I need to find B. So using the first one, first set of data right here, we can apply this into the problem. So P is equal to 1, and A is A because we don't have A. We don't have B, but T is equal to 0. Oh, okay. That's easy. So then 1 is equal to A times 1. So that means A is equal to 1. Now it makes sense. Remember I say A is always the initial condition. So if our initial condition for this problem takes place in 1822, because we set T equal to 0 in year 1822, then whatever that value is for T equal to 0 is indeed A. Perfect. So we apply this, then our equation turns out to be P is equal to 1 times B to the T. Okay, so we chip away the problem a little bit at the time. So we got A, now we need to find B. So now we need to take the second set, and then we need to apply and put it into this equation. Okay, so P now in this case is 8. 1 is still 1. B we don't know, but T is equal to 200. Okay, so 8 is equal to B to the power of 200. So what's B then? Well, that means in order to find B, we need to get rid of the exponent to the 200 order, right? 200 power. Now, in order to do that, to get rid of that, is to take the root of 200, right? So to the power to the if you have B squared equal to 4, then you take square root. If you have B cubed to the 9th, you take cube root on both sides. In this case, it's B to 200, so you take the 200th root on both sides. So in a sense, B is equal to 200th root of 8. Now, you don't know what that is, but you can use your calculator. Calculator is very convenient. It's very helpful. So in a calculator, this basically is 8 to the power of 1 over 200. So in a calculator, this is what you type in: 8 to the power parenthesis. Make sure you put parenthesis 1 over 200. Now that should give you, if I type in correctly, that should give you 1.01 ... some sort of decimal over there. So that means I then can write this down. P is equal to A is equal to 1. B is equal to 1.01 parenthesis to the T power. So now this is my answer for part A. This is a particular equation. Now, if I want to be super accurate, then I will actually just put ... here, ... signaling that the decimal values will continue. It doesn't really matter. I mean, for the purpose of just be able to show that you can demonstrate understanding of this problem, this is fine. So that's your part A. So part B, if part B asks your question, hey, what about in 10 years? Aren't you curious that in 10 years, how many people will we have in the world? So what would be what is the population? What is P when year of 2032? So that might be that's the next question. So you say, okay, well, if that's the case, what we want to find, really what we're looking for is we're finding P when T is equal to what? Well, if 2022 is 200, T equal to 200, then 2032 is 10 years on top of the 200, so T is equal to 210, isn't it? Right? This is representing year 2032. So that means we need to take that equation, P is equal to 1 times 1.01 to the 210th power. Now you can just use your calculator, and I won't solve it for you right now. I will solve it for you using calculator. I already did it. You end up with 8.081 ... Now, of course, you want to make sure you have a unit, billions of people. So that means in 10 years, it's close to, you'll increase by 81 million people, right? 81 million people. This is the increase, because you grow from 8.8 billion to 8.081 billion. That's a lot of people. Now, let's take a look at this, right? If this is a particular equation right here, So what is the growth rate? C. What is the growth rate? Well, if you look at this, our particular equation is P equal to 1 times 1.01 T. And the general equation, y is equal to a times 1 plus r to the t power. Then r must be 0.01 or 1%. So that means the human population of the world is growing roughly around 1%. If you Google the growth rate of world population, I think is the last time I checked was roughly around 1 point something percent. So it's very close. So this is actually pretty accurate. Okay. All right. Now next problem, and this will be the last problem in this particular video. Example 3. In this case, say for example, this is the problem, 2015. In 2015, you have received, so hypothetically, you have received 1,000 emails. And I think you're very popular, or that you hold a very important professional position, and you're growing in your profession. And by 2016, you end up with 1,400 emails for that whole year. So the question here is, you want to write, it's asking you to write a particular equation of number of emails you will receive in terms of times, with the initial year in 2009. Oh, wait a minute. So it actually goes back a little bit more. So it's 2015. You would think that because the problem is given you this way, then 2015 is your initial year. But they want your initial year to go a little further back to 2009, right? So that kind of makes it a little complicated. But no fear. Again, I go back to try to organize my thoughts by putting this data together. So I'll do year again, year, T, and Y. Y is the number of emails. Y is emails. And I will actually go back to 2009, 2010, 2011, 2012, 2013, 2014, 2015, 2016. So number year 2009 will be 0. Year 0. 1, 2, 3, 4, 5, 6, 7. Okay. So and I have no idea what these values are up all the way until year 6, right? T equal to 6, which gives you 1,000, and the next year is 1,400. So now I need to figure out what's the rate, right? The rate. So if you think about it, there's an increase of 400 emails from 1,000 emails, right? So the rate, right? So the rate is 400 emails. That's in addition, right? That's 400 additional emails divided by 1,000 emails in 2015, right? So this gives me what? This gives me 0.4 or 40%. So if you think about it, that makes sense. So then we know that immediately we know that if this follows the growth model, y is equal to a times b to the t power, and this is a growth model. Then this is y equal to a times 1 plus r to the t power. Well, since we know that r is equal to 0.4, then we have y is equal to a times 1.4 to the t power. Oh, I'm closer to the solution, the answer, because I got a. Oh, I got b. This is our b, right? This is our b. So now the question is, what is a? And we want a to be going all the way back to 2009. 2009. So in 2009, which means t is equal to 0, we want to figure out what y is. Right, y is. Right. So let's take a look at this. Actually, we don't need to do that. Right now what we need to do is we can utilize what we have. And well, in this case, this is in many ways because we want to figure out the initial condition, right? This is in dA, right? Y is in dA at t equals 0. But what we can do is we can take a look at we can use numbers in 2016. So in this case, 2016, we got 1400 is equal to A, which we don't know, B is 1.4, and T will be 7, right? T equal to 7, Y is equal to 1400 in 2016. So if that's the case, then I need to find out what A is. So A is just 1400 divided by 1.4 to the 7 power. Now we can use calculator. Now let me do that so you can see. So use calculator. You will have 1400 divided by, to see 1.4 to the 7 power. That should give you A is equal to 132.8 dot dot dot. Then you can round it up as A is approximately 133. So that means in this case, I'm going to write it over here. Y is equal to 133 times 1.4 to the t power. This is our particular equation, and this is 133 is our initial condition. Okay? So here you are. Is using exponential function modeling and look at the general form, finding A and B, recognizing what A is, recognizing what B is. And if you can just zero in on that general equation and always think about, well, how do you find that A and how do you find that B, and what is the X and what is the Y, and how that gets adjusted to the particular problem, then you'll be all set.